We are going to discuss what we call homotophy. Now, homotophy is actually a very important topic in what we call algebraic topology. And in contrast with homeomorphism, which we have just discussed when we were talking about deformations of manifold from one shape to another, I gave you example of deforming a donut or torus to a cup of tea, or what we call tea mug. In homotopy, it's also actually a deformation map, but it is weaker in comparison with homeomorphism. Now, I told you homeomorphism is also a weaker tool compared to knot theory. Now, homotopy is also a weaker version of homeomorphism. It is weaker because it is invariant under dimension. In homeomorphism, we preserve dimensions, but in homotopy, we don't bother about dimensions. It is a destructive map. Some call it a weird or destructive types of deformation, where you deform a shape, of course without tearing, but onto another shape which is totally different from the original shape. Is it clear? So maybe before I give you the formal definition, let me give you simple example what I mean. Now consider the real line R from minus infinity to infinity. This real line is homotopic to a single point. Now what is the dimension in R? R has dimension 1. Dimension of R is 1. But dimension of a single point is what? 0. Is it clear? Yes, so that means it is invariant and it doesn't care about this. So up to dimension, it is invariant. Or you can also take example of even Rn, R2 or Rn. You can, what am I doing in homotopy is I'm contracting this line out of point, it becomes just a point. Is it clear? I can also take R2, R, okay? And I can also deform it onto a single point with dimension 0. This dimension of this is what? 2. Yeah, because this R, I have contracted it into a single. I can also take a triangle, collapse it onto a line, and then collapse it again onto also a single. In fact, I can take a whole disk, not this. This is disk. I can collapse it onto a single point. So I don't care. The homotopy map doesn't care about dimension. It is invariant under dimension. That's also some call it a destructive form of deformation. Okay. Now, formal definition. Now, let X and Y be topological spaces. Okay. And let F and G be maps. Okay. We say that F is homotopic as a map on to G if, is it clear? There exists a map, let me call it H, from X to Y, such that, okay, so you write, which you write like this, X under a homotopy H to Y. Remember, X and Y are what? Topological spaces, okay? X, Y are topological spaces, okay? Now, such that there exists a map like this, so I write X, then with X times some I, okay, to Y. So like we can write like this. Where my I is what? A unit interval from 0 to 1. So what I'm doing is I'm now putting a time lag T, which runs from 0 to 1. And I continuously deform my topological X, space X, within the time limit 0 to 1. Up to the time it becomes Y in shape. Is it clear? So that's why I'm putting this I, X plus 1. And so we say Hx to Y, and then with f of x0 equals f of x. F at x and 1 equals g of x. Is it clear? So I continuously deform my x within this time interval so that when I am at 0, I apply f. And I'm continuously, when I'm at 1 over 10, 1 over 8, 1 over, up to 1 over 2. When I reach 1, I apply g of x. Is it clear? Yes, so this is what I'm doing. Let me clear this.